So, welcome back to the course on architectural design of ICs. So, in the last class we are seeing this CORDIC architecture. So, CORDIC has a vast application for the DSP algorithms. Basically, whenever this cost or the area, hardware cost or the area is a major constant. So, at that time we mostly prefer to use CORDIC instead of the in general MAC based that means approaches. Okay. So, we are that means we have used when to use, why we will use CORDIC, and then what is the that means concept of CORDIC that we are basically see in the last class. Okay. So, whenever we are doing this is the nothing but the initial vectors that we have to rotate by some predefined angle to get the desired this rotational angle. Okay. So, how to do that? So, we have seen that suppose we are having one initial vector which is x 1 and x y 1. So, if I just rotate that, if I want to rotate that another, that means the vectors which is being rotated by the desired angle theta. So, that value can be written as this x 2 value can be written as in terms of x 1 cos theta minus y 1 sin theta, and then this y 2 value can be written as this y 1 cos theta plus x 1 sin theta. So, that we have already seen. Okay. So, based on that what we have done, we have, that means we have not used the original rotation, we have used or we have introduced the pseudo rotation. So, what is the meaning of pseudo rotation? Pseudo rotation basically they are being introduced, that means keeping this fact the values will be in terms of this 2 to the power minus I. Means what? Actually, what was my initial equation, that was x I minus, or if x I plus 1 if I write it, or x 2 there we are basically writing in terms of I if I write. So, at the time x I plus 1 that can be written as x I minus, initially it was y I into tan inverse of alpha I, right. But this alpha I that has been replaced by the values of this d I into 2 to the power minus I. So, that means now what I said, predefined values of the angle. So, how we can calculate the predefined values of the angle? So, that means initially or from the beginning we are using this particular set where the alpha or the tan inverse values, that means tan of this alpha I, those values will be dependent on the 2 to the power I, means it will be dependent on the 2 to the power that means this 0, then 2 to the power minus 1, then 2 to the power minus 2, then 2 to the power minus 3, then 2 to the power minus 4, something like this. So, then what will be the corresponding that means values of this tan inverse of 2 to the power minus I? So, we can easily get, that means as this number is basically fixed. So, that means from the beginning, so this I know. So, this number I can write in terms of degree. So, tan inverse of 2 to the power minus I, when I equals to 0 means this is tan inverse of 1 means that is 45 degree. So, tan inverse of 2 to the power minus 1 means that is tan inverse of 0.5, the values is 26.6 degree. So, these are the basic predefined elementary angle which I have to store somewhere to calculate any values of the theta. So, how we can calculate? Suppose this 30 degree angle is my desired angle of rotation. So, how we can do that? So, initially it will be rotated by 45 degree. Okay. So, then based on, actually if I just go to the next slide. So, initially this is the my desired angle is 30 degree. Okay. So, initially it is being, that means the first set of this 2 to the power minus that means tan inverse of 2 to the power minus 0, which is tan inverse of 1, that means it will be shifted by 45 degree. Okay. And basically what will be the direction of that? What will be the direction of that? That basically dependent on the values of this z I, sorry z I plus 1. Okay. So, what I said in the previous class, I said z is basically holds the value that in each of the iteration how much value or how much is the angle I am basically moving. Okay. So, depending on the, that means if the values are coming in the negative, so this now this di value is the sine of this particular angle. Okay. So, if this di equals to, that means if this z is negative, so at that time di will make this particular equation positive and this will become negative. Okay. So, how to do that? So, that means this is the equation, that is x I minus di 2 to the power minus I of y I, and the y I plus 1 equals to y I plus di x I minus into 2 to the power minus I, and z I equals to z I minus di of E I. So, E I in each step it is being calculated. So, initially what is this? This is 30 degree. So, that means 30 degree means this is positive, di is positive. So, this is 1 means 30 is the z I minus di into E I is the elementary angle. So, first elementary angle is 45 degree. So, from 30 degree 45 degree will be minus. Okay. So, z I plus 1 will be, initially it will be, after the first iteration it will be minus 15 degree, because 30 minus 45 is 15 degree, right. So, then this 15 degree will be the next corresponding values of z I. Okay. So, minus 15 comes over here. So, minus of this, now it will become this equation plus or positive, because this is negative means the sign of this will be negative, means negative it will be positive. So, this what is the next secondary elementary angle, that is 26.6. So, then this 15 degree will be added with 26.6, which is this 11.6, this results 11.6. So, now 11.6 is my in the next iteration z I value, current z I value. Okay. So, then as this is positive, what is the next elementary angle, that is 14 degree. So, now 14 degree will be minus. So, minus of this again this indicates minus 2.4. So, 11.6 minus 14, that is 2.4. So, 2.4 again. So, that will be added with that means the next this fourth elementary angle, which is 7.1. So, 7.1, this is plus 4.7, then plus 4.7, that is minus with this 3.6, 1.1 in this manner. So, unless and until I am getting this particular thing as 0, okay, I will try to move the corresponding vectors position in this manner. Okay. So, that means what is that means the final values are like this, and if I consider that means the bit length of, that is 10 bit. If I consider more than this value will be more, and I have to do this iteration more on this. But at the time, as this value is becoming very much less over here, or it is nearer to 0. So, that means I can basically say that okay, whatever value or the corresponding, that means this x I value and y I value I will get at this particular location. So, that will be my desired sin theta and cos theta value. Okay. So, that means we have started with the initial angle and then we are just rotating in this manner. So, here you see initially basically this is this 30 degree shift, then this is minus 45, then this plus 26, then again minus 14, then 7.1. In this manner it will, this vector will just rotate and finally it will just lie on this particular line. Okay. So, it says that the first 3 of 10 pseudo rotation leading from x 0 and y 0 in rotating by plus 30 degree, and this choosing of the sign of the rotation angle in order to force z to 0. So, that means here what is my this corresponding location, that means why this z is intended to be 0, because here what is happening, we are considering the, that means whenever if I just see this equation, okay, if I just see this equation. So, at that time what is z I equals z I plus 1 equals to y, z I minus alpha I. When this z I equals to alpha I, so at that time it will become 0. At that time only I can say that okay, so this is whatever value I am getting, so that value is same as the, that means the corresponding desired angle which is alpha here. Okay. So, that is why we are basically trying to set this value, or this we are just making this z value to 0 or nearer to 0. Okay. So, that means whatever x and y, x I plus 1 sorry x and y value we are getting at this particular this iteration, those values are not correct, because this corresponding z values are not nearer to 0. So, here you see these values is basically currently holding the values of 0, and whatever the x and y value I will get. So, that is the final values of x theta, sorry, sin theta and cos theta. Okay. So, in this manner, and why we have intentionally doing this di introduce this term di into 2 to the power minus I, because 2 to the power I means what? It is being divided by 2. So, in 0 means what? This is 1. So, it is just directly x I minus, in the first iteration it will x I x 1 sorry x 0 minus y 0. In the next it is what? X 1 minus, this is 1 means by 2. So, it will be y 1 by 2. In the third it will be x 2 minus y 2 by 4. Then in the fourth it will be x 3 minus y 3 divided by 8. Why? Because this power of this is also increasing. So, divide by this means what? Divide by this 2 to the power I means just nothing but the shift of the LSB. Okay. So, shift in the, that means in the right direction, if you just do, that means you just discard the LSB position, okay, or shift the data in the right direction, that means in the right direction. So, you will get divide by 2 very easily. You do not require any hardware shifter at that time. That means shifter means any shift register to do that. Only hardware shifting or just that means discarding of the LSB, you will get it. You do not need any extra logic gates to do that particular operation. Okay. So, here only what thing you require, that you require only the subtractor or addition operation. So, that means, okay. So, that means, so this is the, that means the angle. Okay. So, if I just, so if I just, that means summed up this algorithm. So, at that time the algorithm is basically written as x I plus 1, that is equals to x I minus d I into 2 to the power I minus y into y I plus 1, that is y I plus d I into 2 to the power minus I of x I, where z I equals z I plus 1 equals to z I minus d I of the alpha I or theta I, whatever is the desired angle we are choosing. So, these three equation what it requires basically? It requires this 2 shift this 2 shift operation because of this 2 to the power I in these two equation, and then one lookup table. Lookup table means this is the ROM based kind of structure, where we have to store these elementary values, which is nothing but this theta I over here. Elementary angle means whatever is the values of like this 45 degree, then 26.6 degree, then 14 degree, then 7.1 degree. So, this value or this angle value has to be stored somewhere. So, these you need for this theta I value, you need one lookup table to store all these values. And then what you need? You need adder or subtractor operation. Why adder or subtractor? 3 adder or subtractor, because based on this di, it will be either addition operation or shift, that means subtraction operation. If this di value is that means the corresponding value of this is positive. Positive means this will be minus. If this value is negative, so at that time this will become positive, that means addition, this will become subtraction, okay, and this is also addition. So, that means I need one adder subtractor circuit, so where this control will be done through the corresponding sign of this. So, let us consider, so here z I plus 1, when can I recognize this z I plus 1 equals to, that is minus, negative or positive? If I consider the MSB of z I plus 1. So, MSB of z I plus 1 equals to 1 means this indicates this is one negative number, because that is the sign bit. Considering that sign bit, it indicates that okay, if it is 1, so it indicates that okay, this is negative. So, at that time it will be positive, it will be negative. So, if this is 0, so at that time this will be negative, this will be positive, and this will be negative 2. So, based on this, I need, this is not 3 addition, I need 3 addition cum subtraction operation. Okay. So, if you just see the architecture of this particular equation, so here what is there, that means x I plus 1 equals to x I minus d I to the power minus I of y I. Now, what is I? I is the number of iteration I will use. So, number of the iteration, how it depends? It depends on the, that means what is the length of the, that means theta I am using. So, if I use the theta length of, let us consider 10 bit, so that means the 10th is the iteration of what I have to do. Okay. Then if I consider, that means suppose the CORDIC length is of 24 bit, so that means the 24th number of iteration I have to do. So, that means that means it will be done as this 2 to the power minus, that means 2 to the power minus 0 first, then 2 to the power minus 2, then 2 to the power minus 3, 2 to the power minus 4. At the time the lookup table entry will be of 24 numbers, and each of this tan inverse of 2 to the power minus I. Okay. So, here you see, so so whatever is the, that means with this length we are using, so based on that there will be, so at the very first it will I goes to 0 means this stage will be done, then it will be x 1, then it will be x 2, then it will be x 3, up to how much? Up to, if I consider for n bit, so it will be up to x n minus 1, y n minus 1 and z n minus 1. So, what is this? This is basically parallel architecture. Okay. And then if you just consider this parallel architecture, what it requires? It requires this adder subtractor unit. Okay. So, adder subtractor unit, then this shifting operation in each of this, how much bit it will be shifting? It will shift 0 at this particular, 1 at this particular, 2 at this particular. Why? Because you see this 2 to the power I means I is for 0, then for in the first stage it will require 2 to the power minus 1, then 2 to the power minus 2. So, here you see at this is shifted by 0, then this is shifted by 1, this is shifted by 2, and here it is shifted by n minus 1. So, what I said, this is nothing but the hardware shift. Okay. So, you just truncate the LSB. So, you will get the results as divide by 2, divide by 4, divide by 8, something like this. Okay. And then what I require, I need to store these corresponding values of this alpha. So, at the alpha 0, then alpha 1, alpha 2 in the same manner of alpha n minus 1. Okay. So, if I consider n bits, so n entries of ROM lookup table will be there. Okay. So, then if I consider this iterative architecture, so here you see each of the stage is very much similar, and as I am considering this is as a parallel structure. So, that is why it is all the stages are being implemented in one particular, that means in one flow. Okay. But in iterative, in one of this particular stage, now it can be rerun for this n minus 1 sorry n times. If I run this particular one stage n times, I will get the same results whatever I am getting from this particular circuit. So, at that time what will happen? At that time the hardware requirement that will be less. Okay. So, hardware requirement will be less because I have to use only 3 addition operation and this registers and muxes to select whether I have to choose this intermediate results or I have to load the initial x 0 and y 0 value. Okay. So, this muxes is basically once it takes the z, that means initial values of x, y, z, and then it takes another value of the, that means in the intermediate stage. That means from after 0, then again it will choose this, then 1, then 2, that means it runs in a loop. So, then what it, that means the advantage of this particular circuit is that hardware wise it takes very less amount of, that means component. Why? Because here if I need this n minus 1 number of stage, that means, so how many number of addition subtraction I require, that is 3 into n minus 1. So, that means 3n minus 3 number of this adder subtractor I require over here, but here only I require 3 adder subtractor circuit, and apart from that I need extra 3 marks, which is not required in this case. Okay. So, that is why, but at that time where I am losing, that means this throughput wise it is basically less. Why less? Because I have to wait for the 10th cycle. Suppose here in this particular example we have seen that 10th iteration. So, after that means 10th iteration only I will get the output at this particular location. So, for 10th clock cycle I have to wait. Okay. So, that is why this, that means that is the latency time, or that is the latency of this particular circuit. So, up to that much time I have to wait to get the results of that, though I have put the inputs. Okay. So, that is why this and throughput means what? That it is the time to get the output after applying the input. That means, at what time I have applied the input, at what time I am getting the input, the difference between that, that is the throughput of that. So, here this throughput is basically less, and how many times? It is n time less, because n times it has to, the loop has to run for completion of the whole operation. Okay. And here for this, actually the shifter here, it is not hardware shifter, because in each stage it will be changed. So, I need barrel shifter. Okay. And the barrel shifter is basically, in the hardware shifter what I require? I do not require any logic. Okay. Only the truncation of the LSB, that is sufficient, but the barrel shifter it requires some of the logic to do this. That means, here what is the, in each of the stage this is barrel shifter, or I can say that as a variable shifter. That means, depending on the stage the number of shift operation will be changed. Okay. So, based on that, now this equation. Okay. And so, this is the, that means the advantage of iterative circuit. Cost wise it is advantageous, but throughput wise or this it is not better than this. And here what is the problem in this particular circuit?
as you see, there are n number of stage in any of the path. In any of the path, okay, not any of the path, because the sign of this again it is dependent on this. Okay. Means what? Basically, it will that means dependent on this, the operation of this, again this in that means is dependent, the output of this, or the sorry, this input is basically output from this particular operation. Okay. So, that means, and then again it is passing through n number of stage. Okay. So, that means the as the stage or the iteration number increased in this, so the number of, that means the delay amount is also increased. So, the delay amount increased, if the n is more, so the number of delay or that means amount of delay is also more. So, at that time what I can do, if I put, you see this is one very regular structure. If I make pipeline of this structure, pipeline means in each of these point if I put resistors, actually what is happening here, this is basically totally data driven. Means what? Whenever there is a change, that means whenever there is this x 0 and y 0 this value is available. So, it will immediately, that means after whatever is the delay for this particular adder subtractor, after that time the output will be available over here, then again it will start its operation, then again it will start its operation after this much of delay, then again this, then again after this much of delay again this, something like this, this will run sequentially, considering only the delay of this. But from the data driven of this particular circuit, so that is why this is purely combinatorial circuit. So, that is why this circuit is basically data driven. So, instead of that, if I put in this particular intermediate point, if I put resistor, that means this point if I put resistors, in this point if I put resistor, in this point if I put resistors. So, at that time this will be broken because of this particular resistor, and at that time from the data driven property of this circuit, now it will depend on the clock driven. So, in each of the stage now they will not be adjacent to each other, they will be independent to each other. That means, this particular stage will execute at, if that is at 0th clock cycle, this will be execute at next clock cycle, which is 1 clock cycle or the first clock cycle. Then this will be executed at the third one, this will be executed at n minus 1 time, that means 1th clock cycle. Okay. So, in this manner this will be changed, and at that time the delay will be lesser. So, delay will be just only this adder subtractor, that means that is will be dominated by mostly this adder subtractor delay. Okay. So, that means at that time my area will be more. How area will be more? As I have to introduce again 3 n minus 1 number of extra resistors to do that, but speed wise it will be on the hash side. Okay. So, that is why for it is dependent upon you whether you have to use this pipeline CORDIC. So, at that time this structure will be named as pipeline CORDIC. So, pipeline CORDIC architecture you have to use. So, pipeline CORDIC architecture means cost wise it is not that much, that means the constant is not that cost. If you want to improve the that means the speed of operation. So, at that time you make it pipeline CORDIC. Okay. But if you want your cost as a major constant, so at that time this architecture is very much efficient. You follow this architecture, obviously the throughput will be lower, but area wise this is has the most advantages. Okay. So, for today, so this is not only the fact that okay, after this is the hardware I am getting. So, this is not only the fact that after doing this pseudo rotation or this equation I am getting it, but there are several other terms also, and what I said that many of the arithmetic operation we can perform using CORDIC. So, how we can do and what are the other things which are associated with the CORDIC. So, that we will see in the next class. So, thank you for today's class.